All right, 2.5, 2.6, and 2.8 in your book are going to talk about what the atom looks like, and also going to talk about naming compounds that are the combinations of multiple types of atoms. So quickly, as we've learned in the past, this is kind of what an atom looks like as you see the picture in front of you. We have a nucleus in the center, and we have an electron cloud, and the electrons live in this pink area, this cloud around the nucleus, and they spin around the nucleus at average positions. And it's the electrons that are involved in the bonding of the atoms to make the larger molecules. So just to recap how we actually count the number of subatomic particles inside of an atom, I want to take a look at specific types of atoms called isotopes. So if we call isotopes are atoms with the same number of protons but different neutrons. They show identical chemical properties. And in nature, most elements contain a mixture of isotopes. So oxygen, for instance, there's multiple types of oxygen. They all react chemically similar, but they have different numbers of subatomic particles inside of their nucleus. Let's take a look at sodium, for example, and we've got an accelerated or a blown-up view of the nucleus in the bubble, and you'll notice that we have a different number of neutrons in the left than we do on the right, 12 and 13. But the main point here is to understand that this is still sodium, and chemically speaking, both of these atoms would react the same. Now, where do isotopes come into play? Well, they certainly come into play when it comes to nuclear chemistry, when you're talking about maybe a nuclear reactor. So let's do an exercise problem. If we had a certain isotope, we're not going to name it, that contains 23 protons and 28 neutrons, we want to know what the mass number of this isotope is, and this will help us to find mass number. And then we also want to identify the element. So let's think about that. The mass number is 51, and by definition the mass number is just the addition of the protons and the neutrons. This number can change, and it can change while staying the same element. We can still have the same element. And if we want to know what the name of the element is, or the identity, it would be vanadium. You may ask, well, how do we know that? That comes directly from this number, the number of protons. Okay? Vanadium is the only element that has 23 protons. If we change the protons, we change the element. On the other hand, if we change the neutrons, we don't change the element, we just have a new isotope. All right. So let's move on to 2.6 now, where we talk about molecules and ions. Well, what makes a molecule? A chemical bond makes a molecule, and we have multiple types of chemical bonds. First, we have covalent bonds, which we've talked briefly in class about. This is atoms that share electrons. This resulting collection of atoms we will call a molecule. And covalent bonds are partnered or coupled with a second type called ionic bonds. Ionic bonds are formed from the attraction between oppositely charged ions. We have two types of ions. Ions are atoms or groups of atoms that have a net positive or negative charge. Those two types of ions are cations. These are positively charged, so they've lost an electron. The other type of ion is an anion. These are negatively charged, so they've gained an electron. And it's this relationship that the College Board is very persistent with you understanding, and it's going to carry with you throughout each chapter that we try and study. And it's a little bit misconceiving because you think if something gains an electron, it becomes more positive because it's adding something. But remember, it's not the number of electrons that's so important. It's the charge of the electrons, charges. Electrons are always negatively charged. So if you're gaining one, you're becoming more negative, and that's where the negative ion comes into play. All right, let's look at another exercise. We got another isotope this time. And its symbol is X with a plus in the upper right-hand corner that contains 54 electrons and 78 neutrons. So we have to know what that plus sign means in the upper right-hand corner. First, we're going to ask what's the mass number of the isotope. And second, we're going to ask, we'll get to that later. The mass number is 133. Again, how did we get that? Just simply adding up the number of neutrons and protons. Well, you may ask, well, how do we know the number of protons? Let me go back here. How do we know the number of protons? Well, if we had 54 electrons to start out, 54 electrons, okay, but our element we're specifically talking about is positive, that means we had to lose one electron. So minus one electron, that equals 53 electrons. That's how many electrons it would take for this particular element to be stable, have the same number of electrons as, that's right, protons. And as we said in the previous slide, it's the number of protons that dictates the element. Okay, now, how do we find a mass number? Well, it's just 53, number of protons, plus 78, number of neutrons. And if you do that math, you're going to get 133. I think I did my math wrong. There we go, 131. Sorry about that, group. Alright, so we can use the periodic table to actually predict where we're going to find anions and cations. Right. Anions are always going to be located here on the left side of the table, and it's divvied up by this little black line. You guys probably remember this, I'm assuming, from last year. So everything on that side of the line is going to tend to form positive ions or cations. So they're going to want to lose electrons. Everything on the other side is going to want to gain those electrons, so these are anions. So the periodic table is predominantly positively charged. Sorry about my anions there. Alright, and we'll do some demonstrations with that in class when we get to that point. Alright, there are some common charges that groups of elements do have. Alkali metals, that is the very first column on the periodic table. Okay, that includes hydrogen all the way down. Typically have a 1 plus charge. That means that they want to lose an electron. So sodium and lithium and potassium want to lose an electron. Hydrogen's a little goofy. We'll see that in a little bit. Alkaline earth metals, the one next to it, so your magnesiums and calciums, etc., all the way down, they have a 2 plus charge, meaning they want to lose 2 electrons. On the other side of the periodic table, you have the halogens, so chlorine, fluorine, bromine, all of those individuals. And they want to gain 1 electron. Okay, they want to gain 1 electron. And let's remember why they want to do that. I guess that's important too, is to become stable and have a full outer shell of electrons, a stable octet. And then finally the noble gases, the neons, okay, the helium would be up there. Heliums, neons, argons, kryptons, they have 0 charge. So what does that mean about them? That's right, that means that they're non-reactive. They're, as we call it, they're inert. They don't react. Okay, so that's 2.7. Alright, so like I had said earlier, I believe in the term, I said elements by themselves are rather mundane. They're blasé. They don't give us a lot of stuff. And it's not until they start to combine that they become really interesting. And what we're going to need to do is to have a super good handle on the way that compounds are named. We're going to have to know that because you're not always going to be given the name of a compound. You may be given its symbols, or vice versa. You may be given the symbols and you have to know the name. A binary compound is the first and the most simple type of compound. It's composed of only 2 elements, and ionic and covalent compounds are included in these types of simple compounds. So you have a binary ionic compound. The way to recognize those is they contain a metal and a nonmetal, where a binary covalent compound contains 2 nonmetals. So an example of the binary ionic compound would be potassium iodide, potassium being the metal. Okay, the covalent compound might be carbon monoxide. Neither of those are metals. Alright, so that means that it's covalently bonded. And again, we'll do some demos in class to really harp on covalent and ionic. Now there are a couple of compounds in AP chemistry you're going to have to recognize that we're going to use common names only. And these are 2 of the big ones. Water we know. But NH3 is known as ammonia. Alright, and you're really going to have to commit that to memory almost, because you're going to see it so often, especially when we get to acids and bases and redox chemistry. Alright, so our first type of naming compound, again, we're going to start with binary, and we'll start with the simplest, which are binary ionic compounds. Now the cation is always named first, and the anion second. A monatomic cation takes its name from the name of the parent element, monatomic, single atom. The anion is named by taking the root of the element name and adding "-ide". So those are rules. Let's give some examples. KCl, potassium chloride. Notice that the K, we all know that that's potassium. Alright, that doesn't change, but chlorine does change. The change comes in the suffix, and that suffix is "-ide", I-D-E. Two more examples. Magnesium bromide and calcium oxide. Okay. One nice thing to point out about magnesium bromide, a lot of people will tend to call magnesium bromide magnesium dibromide because of that too. But in a binary ionic compound, those subscripts don't get talked about. We don't have to state them. Reason being is because we know what they are. How do we know what they are? Well, let's think about how we formalize compounds, and we'll get to this in more depth tomorrow. As I said earlier on, magnesium is an alkaline earth metal, so it has a 2+ charge. Bromine, being a halogen, has a 1 negative charge. So how do we know what they're going to form? Well, we crisscross the charges to give magnesium bromide. You might be wondering, well, why do we crisscross the charges? Again, we'll cover that in class. Okay. One last thing to notice, and I kind of goofed up on this. When you're writing in a paper, in a research paper, unless an element or a compound starts a sentence, you do not use a capital letter. They're not proper names, so it should be lowercase. Alright, that's it for today.